Problem 3 in homework 21, and we have this doohickey made in the mechanisms class that I teach in the spring, and lengths that we see are all 250 millimeters for each of these different segments of this thing, and the mass of this bar is 3 kilograms and the mass of this is 6 kilograms, and the spring has a stiffness of 140 newtons per meter, and in the position shown is stretched 150 millimeters. And okay, so the wheel within this slot is frictionless, as are the other pin joints, and there's this external moment being placed here of 12 newton meters, and we want to find the angular velocity of BCD when it crosses through the position theta equals to 0, right? So a lot of things going on here. This is I like this because it has a couple of, it's not necessarily, is it, obvious in the beginning, all the things that you're going to have to do. So I have to ponder this a bit. So first off, it's in the vertical plane. This is going to move and get straight. So we might want to even just let's just see what it looks like and then get some dimensions maybe of things we might want to know when it's in the position that we care about, right? The second position. Okay, so right here is the center of this piece. Here's that pin right in here. So for one thing, right, so here let's ghost in what it originally looked like, maybe. We're ghosting it in here, like that. Something like that. If that's 45 degrees, that has to be 45 degrees. So this actually has to be 90 right here in the beginning. So this is actually perpendicular to the thing, right? So this is where it kind of starts out, and that's where it ends right there. So I want to find the distance that this thing makes right here. So I don't know that actually went to there, but this is something I need to know right in there. I need to know that height difference between there. So in order to do this, maybe we could find what that height is and what that height is, right? So this is 250 right there, millimeters, right across there, and this is 45 degrees. All of them should be 45 degrees, right, everywhere. Right in, let's see, draw the stress center along with this thing. Oh, meant to do on the center. Yeah, something like that. Yeah, like right here is 45 degrees as well. All right, so trying to think as I go through here. Yeah. So this distance right here would be 250 times the sine of 45. So this distance would be 176.8 millimeters right in there. And so this distance is going to be half of that, and so is this. So this is going to be the 88.39 millimeters of travel, right? So we could consider this one the datum. And so this is position 2, right? Where this is like position 1 right there, right? Other things I might want to know, the length originally between here and here is going to be 176.8, right? Times 2. So if the original del was 150 millimeters, then the original length of the thing Okay, so it's being stretched that amount, and its length, original length, should be 2 times 176.8. See, original length is this, and then minus 150, right? So we could say that its original length is 203.6 millimeters. If you get the logic behind that, right? That its length right in here is that 176.8 times 2. But they said it was stretched 150 millimeters, so its actually length is this right in there, right? So that's what it would be unstretched. So in del 2, and now what we're going to do is we're going to figure out the length of the thing right here. So that should be 250, and 250 should be 500 minus 203.6. And so 500 minus that, and we should get 296.5 millimeters. Let's see, what else do we want to try to find here? Oh, I know what I have to do. I have to do a little bit of kinematics. Okay, so let's say this piece by itself, I guess I'll draw in here the center of the thing, right? Is going to be moving at omega, I called it BCD. So it's got this will be VB2, right? Now, this is going to be like a little obvious right in here, but this thing has a velocity coming up this way. So this will be VA2, and here's our VB2. So I'm trying to see what I'm trying to think my way through this thing. I don't think I have to worry too much here. So here is like the line that goes through there, but then the line that comes through here. Okay, so what that really says is that this line intersects right in there. So this is the ICR right here. Right? I think that's the conclusion that we have to make. That here's the line that's perpendicular to this, and then here's the and it's traveling through there, right? Yes. Okay. So here's the line that passes through this piece, the velocity that would be here, and here's the line that passes through this velocity. So that has to be the ICR. So at this instant, A pauses. So, but that kind of makes sense if you look at the mechanism, as it's going to reach its peak here, and then it's going to start coming back down once this thing has gone through. So that's okay as the ICR. But what makes this kind of messed up, a little bit messed up, is that now that right there is going to be the velocity of the center of gravity of the piece right there. And I'll just call it VG, right? I don't need to use any other VGs. And also we know this thing has an angular velocity right there of AB, right? And so, like, looking through here, and it's fortunate for us these are the same lengths. So this is actually going to be this. They're going to be equal to each other, even though they're opposite in directions to the thing. But what we have to care about is the motion of the center of this, because this is not a fixed piece. It's flying through the air. All right, it's not flying through the air, but it's translating and rotating. Whereas this guy is just rotating because it has a fixed point. This thing is actually moving. The center of it has a velocity, and this thing is moving, right? So at the instantaneous center, it looks like it's traveling about there. But I'm just trying to be careful. It's kind of fortunate. We probably could get away with, making a mistake and it not counting against us if we just took it as pinned about this one spot. But let's take it right around here. All right, so for the kinematics of this, maybe I'll write this as the kinematics. And this is like the geometry. And for the kinematics, let's say that VB2 is equal to omega BCD times L BC, and therefore omega BCD. No. Yeah, no, we're fine. I don't think that is necessary right there. We also have that VB2 is equal to omega AB. This is going to be up here times L AB, right? So therefore, omega AB, and these are both equal to omega BCD times 0.25. So we could say that omega, I don't need to, I could just state what I happen to be able to observe, right? That they have to be equal to each other. We also say that VG is therefore going to be omega AB LAB over 2, which is also equal to BCD LAB over 2. Right, so there's the kinematics trying to relate everything. I think I got everybody I need here. And then we're going to go the moment of inertia. All right, so I BCD is going to be 1/12 mass of BCD times length of BCD squared, or 1/12 6 times this could be 0.5 squared. So 0.5 squared times 6 divided by 12 is 0.125 kilogram meters squared. I just want to double check that. That makes sense. 0.5 squared times 6, 12. Yeah. And then really the moment of inertia of this other one should just be 1/2 that, I think. No, it's not going to be. Don't want to prejudge. AB LAB squared. Yeah, so it's not going to be 1/2 of it. It's going to be 0.25 because that's squared. And so we get 0.25 squared 3 times 12 divided, considerably less. All right, so I'm going to go with the scientific notation here. E minus 2 kilogram meters squared. All right, so we got a lot of the stuff out of the way. So let's go into our solution here. All right. So this is problem 3, continued, ... I want to have KE1 plus PE1 plus U1 to 2 is going to be equal to KE2 plus PE2. Starts from rest, that's good. PE1. All right, so for what we wanted, we had we're going to start here with the datum because this one moves position, so its center of gravity is higher at at state 2. So state 1 for the gravity aspect of it is the datum, so it's 0. But we still have spring, right? So the del, we have to take care of that. So it's 1/2 K del 1 squared. And the K was 140, and the del 0.15 squared. So 0.15 squared, 140 times 2 divided, and we're left with 1.575 Newton meters. Now, the work that's being taken place, the external, is going to be because of this moment. And we want to take a moment times our delta theta. Right? So this is a case, this is a constant moment. What angle does it go through? Well, it went to 45 to it closed up. So it traveled through 45. Even though it's over here, it only matters the angle that is changed. So we got our external moment of 12 Newton meters, and the angle is going to be, we'll take 45, but it's got to be in radians, right? So we have to divide by 180 and multiply by pi. So here's some external stuff that's been placed on there. It's one reason why I picked this problem, and because I wanted to have one that had some amount of moment times, this external work being placed in there, that kind of external work. And it's going to have, now we're going to have several parts here. We're going to have 1/2 I of BCD omega BCD, I guess 2 squared, right? Then we're going to have plus 1/2 I of AB omega AB 2 squared, and then plus 1/2 mass of AB times VG squared. All right, so there's a bunch of stuff going on right here. So 1/2, and here's our 0.1250. This is the thing we're trying to calculate. Plus 1/2, and we know this happens to equal, these two happen to be equal to each other, so that makes that a little simpler. So we could just go ahead and just directly replace it. Now we got to do this guy, 1/2, and then the mass of him is 3 kilograms. But now we need the VG2, which we know is going to be omega BCD times LAB. LAB was 0.25 divided by 2 squared. It turns out that because of this orientation, and that being the ICR, we could have taken the moment of inertia just of this piece about this instead of doing it in 2 parts right there. But we went ahead and did it anyway. So let's see, equals to all of this stuff right in here. Yeah, so I want to go 0.25 divided by 2, which is totally could have written it, and then take a square of it, times 3 divided by 2, right? And then I can add that to that divided by 2. There's not a whole lot. And then I take 0.125 divided by 2 and then add it in. So I think my total, I don't like that. 0.125 divided by 2. All right, 0.0625. And then I'm going to add in 1.563 E minus 2 divided by 2. Add them together. Okay, and then this last one is 0.25 divided by 2 squared times 3 divided by 2, and add them. I get the same thing. Okay, so that gets 9.375 E minus 2. Omega BCD2 squared. And then the last thing here is PE2. And we're going to have two parts to it. It's going to be M of AB times G times, what did I call it up above? Did I even give it a name? I didn't give it a name, but it's the distance that this thing is moving here. Delta Y 1 to 2. Delta Y 1 to 2. Plus 1/2 K del 2 squared. So here is 3, 9.81. The distance that's going to move is going to be 0.0883, looks like a 9, plus 1/2, 140, and our del 2 we said was 296, so 0.2965 squared. And hopefully the thing actually won't be like negative or something. I don't know. I think we're gonna be fine. I hope it's external stuff, because sometimes these problems get all kind of messy. So 3, 9.81 times 0.8839 times. Right, so that's 2.601. That's quite a lot. I'm concerned. Ooh, that's not good. So I'm not sure that we have enough moment there. I might have to update this problem. I don't like that idea. Might have to. I don't want this thing to become negative, right? Because we're going to add these two together, but this side's going to be subtracted out from there. So it makes me just a little nervous. So we'll see. 0.2965 squared. All right, so let me do that again. 0.2965 squared. Oh, I got it right. 140 times 2 divided. Yeah, this is going to be bad. What is that? How did I get that? All right, so let me look at it again. I screwed something up. 3 times 9.81. Boom. Times 0.8839 times. So that's 2.601. 0.2965 squared, 140 times 2 divided. Ooh, that's a lot. Plus, comes up to 8.755 Newton meters. So you can see what what's bothering me right here is that we're going to have, putting all these back into here, we have 1.575 plus, I want to double check that that's as small as I think it is. I think this needs to be a larger number. Hopefully I made a mistake right there. 45 divided by 180, right, times pi. Yes. Good. Times 12. Yes, that's the thing. All right. 9.425. Great. Okay. So 9.425 equals 9.375 E minus 2 omega BCD2 squared plus 8.755. Okay, so we should be fine. I'm going to add 1.575 to that. Yay, I get 11. Exactly 11. And then 8.755, I subtract that out, and I end up with 2.244. Let's see if we can find that guy. Nope, gotta punch him in. 9.375 E2 minus, and I have to divide it and square root it, and we get 4.893 radians per second. This is also one I could do a dynamic simulation in SolidWorks on if I wanted to, but not today. Answer. Boom. Omega BCD2 is 4.89 radians per second, and turn it into a vector. Ta-da! We're done. There's a complicated problem. I liked it. It was a good one.